Welcome to Structure for Architecture. In this video, I will discuss about the design of the double reinforced beam. Hope you have seen my other video on the double reinforced beam. In that video, I have discussed how to find out the moment of resistance of a doubly reinforced beam. In this video, I will discuss about the designing of the double reinforced beam. So let us have a look at the steps first. After that, I will take one numerical and then solve it for the designing purpose. So first step number 1 is we have to find the limiting moment, that is Mu.lim, which is given as 0.138 FCK BD square for Fe 415 steel used, 0.139 FCK BD square for Fe 550 steel used, 0.149 FCK BD square for Fe 250 steel used, where B is the width and D is the effective depth of the beam. Now, if the applied moment on the beam is more than this Mu.lim value, then we go for a double reinforced beam. In the second step, this is one table given in IS 456. Let us have a look at the table. In the left hand side column, it is FCK, that is compressive strength of the concrete. It is Newton per mm square. So here it is M15, M20, M25 and M30 concrete. So these four grade of concretes are there. And along the horizontal row wise, it is the value of 100 P.lim. P.lim is the percentage of the steel provided. So this is also again categorized between three steel used. One is FY 250, then 415 and 500. So from this table we have to find out the value of PT, that is the percentage of the steel reinforcement required for the beam. For example, if we are using Fe 415 steel and M20 grade of concrete, which value we should take? First you go for the M20 concrete. What is the FCK? 20. So go horizontally from 20, and which is the steel grade used? That is Fe 415. So 20, along 20 you go in the right hand side of the along the row wise, and then you will get under 450 it is coming as 0.958. So we will use the PT value as 0.958. So this is the way how we should read the table. Now reinforcement for Mu.lim. The first step we have found out Mu.lim. Now the second step is that after finding out PT value, P.lim value, so reinforcement required for this moment is equal to AST1 is equal to P.lim into BD. Step number 3. Now you should find the applied bending moment. As you already know, if it is a simply supported beam with UDL, it is WL square by 8. If it is a cantilever beam with UDL, then it is WL square by 2. This is the basic of bending moment value. So applied bending moment, you can find it out from the problem given according to the span and the loading given. So additional moment can be found out. Mu2 is equal to what is the applied moment, that is the applied on the beam, minus the Mu.lim. So this will give you the additional moment. Actually for this additional moment only we have to go for the double reinforced beam. Otherwise we have to increase the depth of the beam for a single reinforced section, but for that case what happens, sometimes there is a restriction in increasing the depth for some aesthetic purpose or the architectural point of view. We cannot increase the height of the beam, depth of the beam. So that's why we go for a double reinforced beam. So what is the excess moment that is there? For that we have to give the steel in the tension zone as well as in the compression zone also. So how to do that? Let us see that now area for this additional steel reinforcement is AST2. That can be found out by the additional moment Mu2 divided by 0.87 Fy within bracket D minus D dash. What is Fy? Fy is the strength of the steel, D is the effective depth, and D dash is the clear cover. Generally we assume it as between 40 to 70 millimeter. Next, we have to provide the steel reinforcement in the compressive zone also. So how to find out the area of the compressive steel reinforcement? ASC is equal to again that additional moment Mu2 divided by FSC minus FCC within bracket, then multiplied by within bracket d minus d dash. Here FSC is the stress in the compression steel, FCC is the stress in the concrete at the level of the compression steel, AST, okay, no, that's okay. Now FCC can be found out by the formula. This is also given in IS 456, 0.45 FCK. Okay, and how to find out the FSC? So this table is given in SP16. So from the SP16 code, this is the table how to find out the FSC. You can see, I will explain you. See, the first row is d dash by d, that is the effective cover divided by the effective depth. That ratio first you find it out. So that values are given in the 4 values, 0.05, 0.1, 0.15, 0.20. Okay. Now left hand side column, different steel grades are given, Fe250, Fe415 and Fe500. From this table, by interpolation method, we have to find out the value of FSC. If the value of d dash by d directly comes at 0.05, 0.1, 0.15, we can take directly that value. For example, if d dash by d is equal to 0.1 and we are using Fe415 steel, what will be the value of FSC? FSC will be 352. For example, d dash by d is equal to 0.20 and we are using Fe250. Which value? What will be the value of FSC? 217.5. But if suppose the value is coming as 0.08, so it falls between the value between the 0.05 and 0.1. So we have to interpolate and find the value of FSC in that case. So this completes the step number 4. So now let us have a look at the numerical and solve the problem. Let us look at the problem. Design a double reinforced beam of 300 by 600 millimeter overall depth for an effective span of 5.85 meter, subjected to a UDL of 50 kilonewton per meter. Assume the effective cover as 50 millimeter and use M15 concrete and Fe415 steel. Step number 1, first we find out the applied bending moment. So applied bending moment MUD will be WL square by 8. W is given as 50. Effective length span is given as 5.85. So that gives us 213 kilonewton meter. So we should convert it into Newton millimeter because all the parameters that is the strength value are given in Newton millimeter. So kilonewton to Newton 10 cube, meter to millimeter 10 cube. So 10 to the power 6. So 213 into 10 to the power 6 Newton millimeter. Now overall depth is given as 600 millimeter, that is capital D. Let clear cover is equal to 50. Now effective depth will be D minus D dash, that is 600 minus 50, that is 550 millimeter. So now we have to find out the Mu.lim. Mu.lim is what? 0.138 FCK BD square. So FCK value here we are using M15 concrete, B is 300 and D effective depth is 550. So this gives us 187.85 into 10 raised to 6 Newton millimeter. So let us see now. Now as I have explained you earlier, as the applied moment MUD is more than the Mu.lim limiting moment, so here the double reinforced beam has to be designed. So this is one statement, you can write it, though in the question it is given that you design a double reinforced beam, but here you are also checking that value and validating that yes, the double reinforced beam has to be designed for this problem. So now let us have a look at step number 2. As I have explained you earlier that the table I have given, so from the table for Fe415 value and M15, the P.lim value is 0.718 percentage. So reinforcement for Mu.lim will be AST1 will be P.lim into BD. So P.lim is 0.718%, that's why it is divided by 100 into 300 into 550. So that gives us 1185 millimeter square, 1185 millimeter square. Now the additional moment. Additional moment, how we have to find out? Additional moment can be found out by 213. That is the applied moment minus Mu.lim is what, 187.85, then into 10 raised to 6. So that gives us 25.2 into 10 raised to 6 Newton millimeter. So this much is additional moment is generating, for which actually we are going for the double reinforced section, correct? So area requirement, area of additional steel reinforcement AST2 is Mu2 divided by 0.87 Fy into d minus d dash. So that gives us 139.6 millimeter square. Now understand this, that total tensile reinforcement will be number 1 AST1, that is the basic requirement. Even if we go for a single reinforced beam, we go for that AST1, but for the double reinforced beam we are going for this extra area, that is AST2. So what will be the total requirement in the tensile zone? That will be 1185 plus 139.6, that gives us 1325 millimeter square, 1325 millimeter square. Now step number 4, let us now see that how to find out the area for the compressive area steel reinforcement requirement. So ASC is equal to Mu2 divided by FSC minus FCC within bracket d minus d dash. Now see, FCC value is what, 0.45 into FCK. FCK is what, 15, because M15 concrete is used. So it is 6.75. Now what is d dash by d? D dash is equal to 50 and d is equal to 550. So that gives us 0.09. Now I have explained you the table earlier also. So from that table I am just taking these two value for which we need to interpolate. So from the table we are taking the value. So d dash by d is 0.09. So it is coming between 0.05 and 0.1. And what is the steel used over here? Fe415. So which value we should take? 355 and 352. Okay, so now for these two value, now we are doing the interpolation. How we have to do the interpolation? See, 0.05 to 0.1, the difference is 0.05. 0.1 minus 0.05 is equal to 0.05. What is the change in the value? 355 minus 352, that is 3. Now we have to find the value for 0.09. So what is the difference between 0.1 and 0.09? That is 0.01. So corresponding to it we have to find out the value, correct? So if there is a change in 0.05, the value changes by 3. If it is by 1, then it is 3 by 0.05. We are using the unitary method like we have learnt it in the 7th, 8th standard. Like that way only we are doing. Okay, and then 0.01, how much it will be? 3 into 0.01 divided by 0.05, that is 0.6. So actually the FSC value for d dash by d equal to 0.09 will be 352 plus 0.6. Why it is plus? Because you study it. See, actually the value of FSC becomes 355 to 352. It is decreasing. So if because see, from as we proceed from d dash by d value, we are increasing, we are going from 0.05 to 0.1, but the FSC value decreases 355 to 352. So actually for 0.09 it will be 352.6. So now ASC value we can find out from the formula as given above, that is 146 millimeter square. Step number 5, let us assume give 8 millimeter diameter bar in the compression zone. So area of each bar is equal to 50.2 millimeter square. So number of bar required in the compression zone will be, total area requirement in the compression zone was 146. So 146 divided by 50.2, so that comes out to be 3. Now as the tensile zone requirement is more, so let us give 20 millimeter diameter bar. So area of one bar comes out to be 314 millimeter square. So number of bars in the tensile zone is equal to 1325. That was the total area requirement. We have found out is step number 3, divided by 314, that comes out to be 4. So give 4 number of 20 millimeter diameter bar in the tensile zone. and 3 numbers of 8 mm diameter bar in the compressive zone. Total depth is 600 mm, width is 300 mm, and effective depth is 550. So this completes the diagram. Hope you have liked my video, understood it. If you have any comment or any question, please put it in the comment box. If you liked my video, then please share it with your friends. Subscribe my channel for further updates, and thanks for watching.